Good afternoon. Today we're going to be explaining lesson 4.2 trigonometric functions and lesson 4.3 trigonometric applications. This video was done by Gabriel Velasquez and Rolando Wong. We have the six trigonometric functions. We have the sine, the cosine, the tangent, the cosecant, and the cotangent. We will abbreviate them as the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and the cotangent of theta. First, we must understand that the inputs for these functions are always angle measures, as in theta, and the outputs are always ratios. We are now going to find the ratio for each of the trigonometric functions in a triangle. In a triangle, you will be given the angle theta and the lines adjacent, opposite, and hypotenuse. For the sine function, it is opposite over hypotenuse. For the cosine, it's adjacent over hypotenuse. And for the tangent, is opposite over adjacent. If you want to remember these ratios, just remember the line SOHCAHTOA. Now, for the last three trigonometric functions, remember that these are the reciprocals of the original three trigonometric functions, so they are exactly the opposite. So the cosecant will be hypotenuse over opposite, the secant will be hypotenuse over adjacent, and the cotangent will be adjacent over opposite. We are now going to identify the six trigonometric ratios for a given triangle. First, we need to identify what each line in the triangle is. So the 6 is going to be our adjacent line, the 8 is going to be our opposite, and the 10 is going to be our hypotenuse. So for the sine function, we will have 8 over 10. For cosine, we will have 6 over 10. And for tangent, we are going to have 8 over 6. And the cosecant, we're going to have 10 over 8. And the secant, we're going to have 10 over 6. And in the cotangent, we're going to have 6 over 8. We are now going to evaluate the trigonometric functions for a given triangle. For this given triangle, we don't have the hypotenuse, so we need to find it. To find the hypotenuse of a triangle, we need to use the Pythagorean theorem. The Pythagorean theorem consists of squaring the two sides of the triangle that are given to you and making it equal to the hypotenuse square. Once you solve this equation, you will find that the hypotenuse equals the square root of 61. With this information, we can now find the trigonometric functions that they ask us for. First, we have the sine of theta. If you remember correctly, the sine of theta is equal to the opposite over the hypotenuse. Therefore, it will be equal to 6 over the square root of 61. If you want to simplify this, you can make it equal to 6 times the square root of 61 over 61. But you can leave it this way. It's the same thing. Next, we're going to find the secant, which is the hypotenuse over the adjacent. This will be equal to the square root of 61 over 5. And finally, we're going to find the tangent, which is equal to the opposite over the adjacent, which will be equal to 6 over 5. We are now going to solve a triangle using trigonometric functions, which means that we are going to find the sides of a triangle. We are already given the opposite side of the angle. Therefore, we're going to have to find the hypotenuse and the adjacent. Let's begin with the hypotenuse. To find the hypotenuse, we need to understand what type of trigonometric function we're going to use. Since we are given the opposite, we are going to use the sine function, which is the sine of theta is equal to opposite over hypotenuse. So our equation will be the sine of our given angle, which is 67, is equal to 16 over the hypotenuse. To solve this equation, first we're going to move the h to the other side of the equation multiplying. So we will have h times the sine of 67 is equal to 16. Then we're going to move the sine of 67 to the other side of the equation dividing. That will leave us with h is equal to 16 over the sine of 67. Once you plug in this into your calculator, you are going to find that h is equal to 17.38. Now we have to find the adjacent side of the triangle. Since we're looking for the adjacent side and we're given the opposite, we can understand that we need to use the tan function to solve for that side, since it's opposite over adjacent. Therefore, our equation will be the tangent of 67 is equal to 16 over the adjacent. We're going to use a similar method to solve this as we did with the hypotenuse. We're going to pass the 8 to the other side of the equation multiplying, as so, and then we're going to pass the tangent dividing in the other side of the equation. Once you plug in this into your calculator, you will find that the adjacent side of this triangle is equal to 6.79. We can also use trigonometric functions to find the missing angles of a triangle. In this triangle, we are given the adjacent side of 9 and the hypotenuse of 18. Using our understanding of trigonometric functions, we can see that we need to use the cosine function to find this angle, since it's adjacent over hypotenuse. Therefore, our equation will be cosine theta equals 9 over 18. To solve this equation, we are going to use the inverse of cosine to be able to cancel out cosine of this side of the equation. So we will be left with theta equals the inverse cosine times 9 over 18. Once you plug this into your calculator, you will find that theta is equal to 60. Therefore, our angle is equal to 60 degrees. Now we're going to use what we learned from trigonometric functions to solve a real-world problem. So, Ms.Long went to France to see the Eiffel Tower. She looked at the top of the tower, which is 301 meters tall, from an angle of 35. How far is she from the tower? Well, first we have to sketch our drawing. They tell us the tower is 301 meters tall, and that she's looking at the tip of the tower from an angle of 35. Now, this very closely resembles all the triangles that we've been working on, and in this case, we're looking for the distance. If you look closely, you can see that the variable x is the adjacent side of this triangle, so we only have to find for that side of the triangle. So, the tangent of 35, since 35 is our angle, is equal to 301 over our adjacent, or x. Once you solve this using what we learned about trigonometric functions, you're going to find that the adjacent side is equal to 429.87 meters. Therefore, our answer is that Ms.Long is standing at 429.87 meters away from the Eiffel Tower. Now we're going to look for an angle using trigonometric functions and a real-world problem. So Ms.Long went to France to see the Eiffel Tower. She looked at the top of the tower, which is 301 meters tall, from 226.80 meters away. What is the angle she was looking at? So first, we need to sketch the information that was given. We were told that the Eiffel Tower is 301 meters tall, and that she is looking from 226.82 meters away, and that we're looking for the angle. Therefore, using our understanding of trigonometric functions, we can see that we are given the opposite and the adjacent side of the angle. Therefore, we are going to use the tan function to solve for the angle. To solve for the angle, we need to use the inverse of the tangent so that we leave theta alone, like so. Once you plug it into your calculator, you will find that theta is equal to 53. And that is the angle at which Ms.Long is looking to the top of the tower from 226.82 meters away. Congratulations, you are now an expert on lessons 4.2 and 4.3.